Hello everyone, welcome to the video series of Basic Electrical Engineering Lab. So far we have discussed the verification of Kirchhoff's voltage law as well as Kirchhoff's current law. Now we will be moving on to the verification of various DC network theorems. So the first theorem which we are going to verify here is Thevenin's theorem, and that will be our experiment number 3. So the object here is clear to us. Our objective today would be to verify Thevenin's theorem in a given DC network. And for that, we'll be requiring certain apparatus. Like the previous experiments, firstly, we'll be requiring a breadboard. We'll be requiring some connecting wires to interconnect our elements. We'll be requiring a ammeter and a voltmeter, or simply you can use a multimeter. And lastly, we'll be requiring carbon resistor, a few carbon resistors of different values. So let us now quickly go through as to what Thevenin theorem actually is and what does it states. So it states that any two-terminal linear bilateral network can be replaced by an equivalent circuit consisting of a voltage source in series with the resistance, which can be seen from those terminals. Meaning, for example, let us say we are having this complex network and you are required to find out load current IL, meaning current flowing across this resistor. All right. So in place of solving this circuit, what we are going to do is we are going to replace this circuit with a simpler circuit which would comprise of three things. Firstly, a voltage source, a resistance in series with it, and our original load resistance. So what was the use of replacing this circuit with this simpler circuit? Now you can easily calculate the current in this circuit, which would be your load current, with the help of formula VTH divided by overall resistance of this circuit, which would be somewhat like this. Meaning now our task has gotten easier as compared to the complex network. All right. And as far as VTH is considered, VTH is your open circuit voltage between the terminals, and equivalent resistance RTH is the ratio of open circuit voltage to the short circuit current of these terminals. And your RTH can also be measured by looking back into the network from the open circuit terminals by replacing all the sources with their internal resistances. So let us now try to understand as to what steps we are going to follow in order to verify Thevenin's theorem in our given DC network. So our Thevenin theorem claims that whatever current is flowing here across resistance RL, which is your load resistance, will be same in case of Thevenin's equivalent circuit, which is somewhere here, meaning IL measured in the complex circuit and IL measured in the equivalent circuit will be same if we keep our RL same in both the cases. All right. So in order to verify Thevenin's theorem, what we are going to do is, firstly, we are going to measure IL in complex circuit with the help of a ammeter, and secondly, what we are going to do is we are going to calculate IL in equivalent circuit, and we'll check whether these two values are equivalent to each other or not. If they are equivalent, then we can easily say that our Thevenin's theorem has been verified. All right. But before replacing this complex network to a simpler Thevenin's network, we need to find out two more values, which are value of your Thevenin's voltage and value of your Thevenin's resistance. After calculation of these two values, you will be able to find out as to how much current is flowing in this equivalent circuit. Without knowing these two values, we will be unable to find out as to how much current is flowing in the equivalent network. And if we are not able to find out current in the equivalent network, you won't be able to verify Thevenin's theorem for a given complex network. All right. So these are your equations which will be used for finding out load current in the equivalent circuit. All right. So let us assume that this is our given circuit diagram. This is a complex network and we need to identify as to how much current is flowing through this resistance RL. Fine. So what we are going to do is we are going to draw this circuit onto the breadboard and we'll take help of a ammeter to find out how much current is going through in this branch. Okay. So this is what your circuit would look like. So if I talk about practical realization of this circuit, this is how your circuit is going to look like onto the breadboard. So this is our given complex network, or you can say which has been given to us. Our objective was to verify Thevenin's theorem in a given DC network. So this is your given complex network. All right. And we have drawn this complex network onto the breadboard. So this is your resistance R1. This is R3. This is R2. And this is your resistance RL. Okay. So what I have done here is I have removed one terminal of resistance R2 from here and inserted an ammeter in between so that my ammeter comes in series with the circuit. So the current flow of current would be somewhat like this, meaning that current would travel through the ammeter giving us its value, and we'll be able to identify the value of IL in the complex circuit. Now next step would be to identify IL in the equivalent circuit. But before doing that, we need to find out VTH and RTH. Okay, so the procedure for finding out VTH is simple. What you are going to do is you are going to remove your load resistance RL. Okay, so if we were to calculate it theoretically, it would take us some time to calculate it with the help of various theorems, or you can say with the help of various laws or mesh analysis or node analysis. But in case of practical realization, it is quite simpler. What you are going to do if you were to find out a voltage between these two terminals, what you are going to do, you are going to simply put a voltmeter across these two terminals and it will show you the reading of voltage, which will be known as your Thevenin's voltage. All right. So what we have done here is we have taken our complex network and we have simply removed our load resistance RL, and we have named those terminals as terminal number A and terminal number B, and we are interested in finding out the voltage across these two terminals, and that voltage is simply known as your Thevenin's voltage. All right. So this is how your circuit for calculation of Thevenin's voltage would look like. Fine. This is your voltmeter. The source is connected to resistance R1 and another terminal is going here. What we have done is we have simply we have removed resistance RL and simply put a voltmeter across those two terminals, and whatever reading this voltmeter gives, that will be our Thevenin's voltage. We are going to write it down and we'll proceed to next step. Next step would be measurement of Thevenin's resistance. So the steps required for measurement of Thevenin's resistance are simple. All right, what you are going to do is, firstly, you are going to remove your load resistance, and secondly, you are going to replace all your sources in the circuit with their internal resistances. Meaning, if there is a voltage source, you are going to replace that voltage source with the short circuit. So try to remember, in the first circuit there was a voltage source here, but what we have done is we have removed this voltage source for the connection diagram of measurement of RTH. So you can already imagine as to how this would look like onto the breadboard. We are going to need a simple connecting wire to just short circuit those two terminals. Earlier, these two terminals were having voltage supply connected to them, but now in this case what we have done is we have short circuited those terminals, meaning that we have replaced our voltage source with the short circuit, and now we have taken a multimeter which is set in the value of resistance. All right, so whatever the value of resistance is being measured here will appear onto the multimeter. All right, or you can simply just calculate it manually also, meaning you can clearly see that this and this resistance are in parallel with each other and their combination is in series with this resistance. All right, so either way you will get the same values. Either you can calculate with the help of multimeter or you can calculate it manually also. All right, so this is what your Thevenin's equivalent network would look like. Once you have these two values, you are going to put these two values here, and you are simply going to calculate IL with the help of formula VTH divided by overall resistance of the circuit. Meaning your first circuit, which was complex circuit, has been replaced with this simpler circuit. Now if we proceed with general instruction, what should we have done? We should have drawn this equivalent circuit onto the breadboard, and we should have inserted a ammeter here, and we should have calculated the value of IL. But every time it is not possible to get the exact value of RTH, meaning that in labs it is not always possible that we have the same value of resistance available with us. For example, let us say that RTH comes out to be 552 ohms. So it would not be possible for us to get a resistance of 552 ohms. So therefore, what we are going to do, instead of practical realization of this equivalent circuit, what we are going to do is we are going to utilize this formula to calculate IL in the equivalent circuit. Okay, so you can mark it with IL dash also, so that you don't confuse it with the current which we have calculated in first, or you can say complex circuit. All right, so this is also your practical value because we have calculated VTH practically and RTH also practically, and RL was also known to us in the initial stages. Okay, so let us quickly go through the procedure once again. Firstly, what you are going to do is you are going to connect the given circuit diagram onto the breadboard as shown in figure. All right, so this would be your main complex network. What you are going to do is you are going to take your resistors, take your breadboard and connect this circuit onto it. All right, and one more important thing you are going to do is you are going to note down the reading of ammeter, which is the load current in the circuit. You are going to insert a ammeter in between, and you are going to measure a current which will be known as IL for your main circuit, or you can say your complex circuit. All right, Secondly, find the open circuit voltage across the terminal AB when load resistance is removed. So in the previous figure, what you are going to do is you are going to simply remove the load resistance and then connect a voltmeter across those terminal and measure the voltage across it. That will be known as your Thevenin's voltage. This would be your step number 2. Your third step is concerned with measurement of Thevenin's resistance. One more additional thing which you are going to do is you are going to replace your voltage source with a short circuit like shown in this figure. And you are going to connect a multimeter here, and that will tell you the reading of equivalent resistance as seen from these two terminals. This will be your RTH. And lastly, what you are going to do is when you have the value of VTH and RTH, you are going to follow the instructions and put them onto the equivalent circuit. So what you are going to do is compute the current flowing through RL in this equivalent circuit. This will be your equivalent circuit comprising of RTH and VTH and RL, which is same as your first step, by using which formula? By using this formula. And if this comes out to be equivalent to your current calculated in the first figure, then you can say that Thevenin's theorem has been successfully verified. All right, let us come to the observation table here. Your first column always remains same. This is your supply voltage. We have named it as VDC. Second column here is your load current, and for which circuit? This is, keeping in mind, this is for your main circuit or your given circuit or your complex circuit. All right, then let us come to RL. RL is the fourth resistance which you are connecting at the end. We'll consider that as RL, and no matter what reading we are taking, your RL would remain same. Only thing which will change in the subsequent readings is your supply voltage. Sometimes it can be 5 volts, it can be 10 volts, it can be 15 volts, it can be 20 volts. All right, next column is your Thevenin's voltage. You now clearly know as to how to calculate Thevenin's voltage. Next column will be your value of RTH, that is your Thevenin's resistance. And once again you are going to encounter IL in the observation table, and that IL will be your from equivalent Thevenin's network. All right, and if this column and your this column are equivalent, then you can say your Thevenin's theorem has been successfully. Let us now move on to the practical realization of Thevenin's theorem. All right, so let us take our given DC network, which looks somewhat like this. So step number 1 would always be identification of resistances which we are going to use. So I have identified my resistances. R1 is 554 ohms, R2 is 237 ohms, R3 is 148 ohms, and RL is, or you can say resistance number 4 is 217 ohms. All right, so in this case I have taken I have omitted theoretical values of resistances, meaning that I have not calculated these values according to color coding, but I have taken the actual practical values which were given to me by the multimeter. So for example, if I tell you the difference as to how much difference is there between practical and theoretical value, if I find out the value of resistance R1 with the help of color coding, it comes out to be around 550 ohm plus minus 1%. Alright, but in case of practical realization, what I need to do is I need to take the actual value of resistance, which can only be given with the help of multimeter. So this is your theoretical value which comes out with the help of color coding, and this is your practical value which I have measured with the help of multimeter. Let's now move on to step number 2. Step number 2 is making this circuit onto the breadboard. So this circuit has already been made. Let us verify it. This is resistance R1, R3 and R2. They all are connected at one node. So let us check whether on my practical breadboard are they connected to each other. Yes, they are connected to each other. Why? Because they are connected in the same column, and we know that all the 5 holes of this column are interconnected with each other internally. Fine. Now let us check whether R2 and RL are connected with each other or not. So I can clearly see here that R2 and RL are connected to each other. Now let us check whether one leg of R3 and one leg of RL are connected to each other or not. So I have taken another rail, which is power rail. I have connected these two legs of resistances onto the power rail, and I can clearly see here that these 5 subdivisions are connected internally horizontally. So I can clearly say that one leg of RL and one leg of R3 is connected with each other. Alright. Now coming on to the power supply, positive end of this power supply is going to where resistance R1 was initially connected. So resistance R1 was connected here. So let us check. Yes, my positive end of the supply is going to R1, and my negative supply is going to where R3 and RL were previously connected. So this is my negative end, and it is going to R3 and junction of R3 and RL. So let us now move on to my step number 3. Before proceeding on to step number 3, let me remind you that our main object here in verification of Thevenin's theorem is that we want to prove that the IL which is here and the IL which could be found in the Thevenin's equivalent circuit is same or not, meaning that whether I take this complex network, although this is not a complex network but this is a simpler network, but for understanding purpose I have assumed this as to be a complex network, and what I have done here is I will calculate as to how much load current, or you can say IL, is going through resistance RL. Fine. So according to Thevenin's theorem, this complex network can be replaced by a simpler network. So what do we need to prove? That we need to prove that when we replace this complex network by a simpler network comprising of VTH, RTH and RL, same amount of current will be flowing across resistance RL. Fine. So therefore in observation table also you will get to see two values of IL. This first value of IL is in the main circuit, and this IL, let us consider this IL dash, will be calculated with the help of Thevenin's equivalent circuit, and our main aim would be to verify whether this IL and this IL dash are equivalent to each other or not. Fine. Then only we'll be able to say that while replacing the complex network with the Thevenin's equivalent network, same amount of current is flowing through resistance RL. Alright. Then only Thevenin's theorem would be useful. Otherwise, if different current is flowing in RL, when we replace it with the help of Thevenin's theorem, then your Thevenin's theorem would fail. Alright. So, our step number 3 would be measurement of load current, or you can say IL, in the main circuit. Fine. And in previous videos we have seen as to how to connect a ammeter for measurement of IL, or you can say for measurement of current. So what do? We break the circuit from here, and we insert an ammeter in series with the resistances through which we want to calculate the current. Fine. So what I am going to do is I am going to break one leg of R2. Let us say this is the second terminal of R2 and this is the first terminal of RL. So what I am going to do is I am going to break the leg and insert a ammeter in between. That is what has been done onto the breadboard. Let us see where is second terminal of R2. This is the second terminal of R2, and after that current will flow like this through one terminal of ammeter, which is here, and then back from another terminal of ammeter and onto RL. Alright. So this is how the connection of ammeter looks like if we want to calculate current through resistance RL. Alright. So I have connected the ammeter here. Let us check as to what is the reading. Let us turn on the supply, and it comes out to be approximately 3.60 milliamperes. I'll note it down. This comes out to be IL in main circuit comes out to be 3.60 milliampere. Now, one thing which you have to understand here is you are taking reading number 1. So you need to also check the first column. First column here is what is the source given to the circuit. Alright. So let us verify as to what is the source which we are giving to the circuit for taking reading number 1. So for doing so, what I am going to do is I am going to connect a voltmeter across my supply. Okay, so I am going to use my multimeter as a voltmeter now, and I am going to connect it across my supply and check as to how much voltage is being supplied to the given. Now your voltmeter has been connected across supply. Either I can connect it in the network or I can directly connect it to the source ports. Okay, so what I have done is I have connected it to the network where my supply was coming initially. So in any case you will get the same answer. So my voltage is coming out to be approximately 10 volts, meaning that I am supplying this circuit with 10 volts, and after giving 10 volts I am getting a current of 3.60 milliampere in the load resistance, which is this one. Alright, if the same current comes out to be 3.60 in case of Thevenin equivalent circuit, I can clearly say that Thevenin's theorem has been verified. Alright, moving on to step number 4. Step number 4 is measurement of Thevenin's voltage. You all must have studied in your theoretical classes as to how to calculate VTH. So for calculating VTH, what we are going to do is we are going to remove the RL resistance. Previously there was a resistance here which was termed as RL. So what we have done here is we have removed that resistance, and now the voltage which we take across these two terminals, let us say this is terminal number A and this is terminal number B, will be known as your Thevenin's voltage. So for measurement of that voltage, what we are going to do is we are going to connect a voltmeter across these two terminals. Alright. So in case of theoretical practices, it is quite difficult to calculate these values because you have to compute it with the help of certain formulas or certain law. But in case of practical realization, it is quite easy. You are simply going to do is you are going to connect one end of your voltmeter here and one end of your voltmeter here. Let us check. One end of voltmeter is going to terminal A, which is connected with R2. Okay, alright. My connections have been made. And another terminal of voltmeter, let us say this is a negative terminal, this is the positive terminal, is going to point B, which is connected with R3, where R3 is connected. So let us see whether it has been verified on to the breadboard or not. Yes, now they are connected with each other. So let us now see as to turn on the power supply and let us see as to how much the VTH is. So the VTH is coming around to be 2.11 volts. So what I am going to do is I am going to note it down as well. Fine. So you might be wondering that in the fourth column there is one parameter left, which is RL. See, you do not have to calculate RL now. Why? Because you did that in the initial step. Your fourth resistance, which was approximately 217 ohm, which you calculated in the step number 1, will always be your RL. Because you are not changing the value of RL here, you have already calculated the value of RL. Alright, so in this manner we have come to VTH, and our VTH is coming out to be approximately 2.11 volts. So moving on to our next step, which is step number 5. What we are going to do, we are going to find out another important parameter, which is Thevenin's resistance. Alright, so what is the procedure for calculating Thevenin's resistance? Firstly, you will remove your load resistance, and secondly, you will replace all the sources in the circuit with their specific internal resistances. So what we did here, we removed the voltage source which was initially present here and replaced it with the help of a short circuit. Alright, if there was a current source present here, we would have replaced it with the help of a open circuit, and we would have calculated the equivalent resistance across these two terminals, which are, let us suppose, which are A and B. Fine. So this is what we are going to do onto the breadboard. What we have done is we have removed RL and we have replaced the source with the help of a short circuit. You can see here we have replaced it with the help of a wire, which turns out to be a short circuit. Alright. So for calculation of RTH, either what you can do is you can calculate this manually also. Okay. So resistances R1 and R3 are in parallel here, and their combination would be in series with R2. So you can find out the equivalent resistance with the help of that method also, but let us here find out with the help of a multimeter. So what I have done is I have turned the knob of multimeter to the resistance portion, and I have connected my multimeter somewhere here. Okay, one terminal is going to point A and another terminal is going to point B, and I can see here what my multimeter is showing. It is showing me 355 ohm, or you can say 0.355 kilo ohm. Alright, so I'll take it in ohms. So I'll write down RTH as 355 ohms. Alright, if you calculate it theoretically with the help of series and parallel combination, it would come out to be approximately 353.79 something. Alright, so
So this much error around approximately 1% or 2% is acceptable. We'll consider RTH to be 355 ohm. So we have gotten the reading for RTH. What I am going to do is I am going to note it down here. So let us now move on to our last and very important step, which is calculation with the help of Thevenin equivalent. So our complex network has been converted into a simpler Thevenin equivalent circuit, which comprises of a voltage source VTH, which we have calculated as 2.11 volts, a resistance in series with it, which is RTH, which is approximately 355 ohms, and a resistance RL, which was in the first circuit as well, which is 217 ohms. Okay, so logically what should we have done is we should have drawn this circuit onto the breadboard, we should have made this circuit onto the breadboard, and we should have calculated, we should have inserted a ammeter in series with RL and should have calculated what is IL dash, meaning as to what is the current flowing in load resistance in case of a Thevenin's equivalent circuit. But sometimes what happens is this value of RTH is uneven. Okay, so we are not always available with the same value of RTH which we have calculated, meaning that resistances which were made by the manufacturers are not always available of the same value which we have calculated. So therefore what we are going to do is we are not going to make this circuit onto the breadboard. What we are going to do is we are going to use our general formula for calculation of IL dash. So IL dash would be what? IL dash would be VTH divided by a combination of RTH and RL. Alright, so in this case what is there? This VTH we have also calculated practically, this RTH we have also calculated practically, and this RL also. So IL dash which we are going to get will also be the practical value of current. Alright, so let us now take our observation table and try to calculate the value of IL dash. So VTH here is 2.11 volts divided by RTH here is 355 and this is RL is 217 ohms, and it comes out approximately to be 3.68 milliamperes. Alright, so meaning that our IL in first circuit is equivalent to IL dash, which was calculated in Thevenin's equivalent circuit, and they both are equivalent. Therefore we can say that our Thevenin's theorem has been verified. Okay, so you can do this verification for a number of readings while changing the supply voltage or while changing the values of resistance which you have taken in first step.